Hello, fellow problem solvers. So today we're going to be doing the problem from the 2025 European Girls Math Olympiad, the geometry problem, problem number 4. I suggest you try this nice geometry problem out for a minimum of 15 minutes, ideally 30-ish to an hour, but I wouldn't go more than 2 hours on this. And it's a very nice introductory problem if you know similarity, if you know angle chasing, if you know how to do the basics really. What's a concyclic quad? You should be able to do this problem. And now, without further ado, let's begin. Now we first start with drawing the diagram. So let's get to it. Okay, let's read the problem itself. What does the problem say? The problem says we're going to have an acute triangle with an in-center. AB is different from AC. We're going to have, okay, BIC intersect the circumcircle. Okay, so the first part here is, okay, we draw the circle. We're going to draw then ABC, so A is going to be up, B and C are going to be here. And the reason we draw A up is because this seems to have some symmetry, and as we continue reading it with respect to A. So BI, the angle bisector, intersects the circumcircle, and CI intersects it as well. So these are points P and Q. Now let's note something about P and Q. So what do we have? We have, first and foremost, let's calculate some angles. So this is how we begin with these problems. So if this is I, let's call this beta half. So let me use different colors. So let's call these angles, let's name them. So beta half, which also makes this angle over here, beta half. And if you haven't seen this before, this implies that AP is equal to PC. Okay, so we move with one step at a time. Gamma half, and then we're going to have also gamma half here and gamma half here. So at every point when you're drawing this diagram, you want to say, okay, you stop as you're reading the problem, you stop and you say, what is it that I have so far? And let's continue onwards now. So this is what we have. We have these equalities, so QA is QB, and we're going to have that AP is BC. Okay, so now we're going to have R such that AQRB, so AQ and then RB is a parallelogram. Okay, so let's think about what this actually means. This means now that this is equal to this is equal to this, so RB is also equal to QA is equal to QC. And then we have some angles we can calculate. So now this angle over here is gamma half. So this one's gamma half, which makes this angle over here gamma half as well. And we're going to have, similarly on the other side, analogously defined, the point is S. And so again, like we're going to have now, this is beta half and this is beta half. Okay, all of these are equal. And now let's think about this. So now I invite you, here you could even pause and try to think about, okay, what is that we have? We have a lot of angles, or we could proceed further. If we proceed further, I mean, we're done with the problem statement, which is to say, okay, SC and RB intersect at some point. So let's say they intersect at some point here, T. And we must prove that RS, TI are concyclic. Okay, so the first order of business in problems such as these is angle chasing. So let's actually draw a different diagram. Now that we know what the problem should look like, let's draw a much nicer diagram for this. So we're going to need a circumcircle. Here, we're going to need to have AB, so we're going to have B and C. Let's draw A such that it's much closer to one as opposed to the other. So now we have ABC. Let's draw BI and CI. And now we have these points. What do we call them? We call them P and Q. And then we have AQ. And here we're going to have the point AQR, B, and APS, C. Okay. Actually, the S point should be over here like this. Okay. So now let's calculate. So we have assumed also here that sort of beta is greater than gamma in the way we've drawn this. So this is beta half, beta half. So let's sort of first try to figure out, okay, what this angle here is. When we have RB, what angle do we have? Well, we have that the angle ABR is equal to 180 minus this one over here, QAB. And this angle over here is gamma half. So you have ABR is 180 minus gamma half. So that means that when we draw T, we will have that the angle TBI will have to equal. So we have this over here is gamma half. So this here is gamma half, which means this angle must be beta half minus gamma half. So I have this is beta half minus gamma half. And I invite you here to pause for 5 to 10 minutes and try to push the problem further. And now that I've hoped that you've paused, I mean, this sort of just tells you, analogously, you should get that TBI is also equal to TCI is equal to beta half minus gamma half. And so now, what can we do with this? Now, what are we actually going to be doing with this problem? So this means that T, B, C, and I are concyclic. Now, isn't that interesting? So now we found that T, B, C, I are concyclic. So there's a circle that goes around here. And we must show that RTIS is concyclic. And note also that this point T, we have that T, B, R are on the same line and T, C, S are on the same line. And now something we do commonly in geometry is we solve the problem forwards or backwards. Now, what would it take to solve the problem backwards? So let's take a step back and see what does it mean when, if this problem was true. So now let's just draw these points. So we have B, we have the point R, we have S, and we have the point C. The other intersection is T, and we have some point I. So what does it mean? So what do we have if these are concyclic? So now, so far we know that this sort of thing happens, that BTS, BTI, and actually BTI and C are concyclic. This is what we know. And now the question is, okay, what would happen if these were also concyclic? So let's take a look at that. If these were also concyclic, well then we would have this angle over here is the same as ICB, is the same as ISR. And we would have that this angle, IST, is the same as IRT. Now, what you find here, and this might be a lemma if you've seen it before, is something called spiral similarity. But basically what it says that we would have that triangles IBR would be similar to the triangle ICS, and the triangle IBC would be similar to the triangle IRS. So now we know that, solving the problem backwards, if the problem statement is true, then we know that we must have this similarity. Now the question for you is, when you look at this picture, like we've found some angle chasing, but is it possible for us to potentially find a similarity? Because if we were to prove that ICS and IBR are similar, then we're done, because then we've proven that, then we have, then we would be basically done with the angle conditions, because then we would have that ISC is the same as IRB. And I mean, that is now what is enough for us to prove. So now I invite you here, again, take 2 to 5 minutes and try to see if you can prove that. And what's important to note here is, for us to prove this, is that we don't even need to think about the point T. Point T has become irrelevant. And it's always a nice thing when you can get rid of a point in geometry. I mean, not always, but like generally, you can always return the point back in case you need it. But it's always nice to sort of have it be that, oh, you have 1 point less that you need to worry about. So now, let's see what we have. We have RS. So we're going to have here point R. And in fact, I mean, we could take this even further to say like what points we need and what points we don't need. The way we define R and S, I'm also curious if we need the other points, if we need P and Q truly to sort of define these parallelograms. But maybe I think, so let's actually think about this. So how is this defined? Well, I mean, we could say that this is defined by the fact that, this is equal to AP. I mean, okay, we don't need to get rid of points right away. Let's see first like what we have. So can we prove, the question is, can we prove that IBCs? Okay, so IBC seems more difficult to try to prove because I don't have anything that connects I and R immediately. At least not immediately. I have some, okay, I have QI, it's the same as QA, it's the same as QB, is the same as RB. Maybe there's something there. Okay, so I don't think we have this. Well, okay, let's see what we do have. We have, if we were to try to prove the similarity, we definitely have, okay, the angle IBR. We can definitely calculate that one. And this angle should be equal to ICS. And my guess is, and I think we can actually go ahead and show this, that it's going to be 180 minus beta half minus gamma half. It's just what it feels like, but I think also because this whole thing is 180 minus gamma, so, right, this angle here is 180 minus gamma half. We have this angle is beta half, so this must be 180 plus gamma half minus beta half, which is exactly what this is. So we have these angles are equal, and we can easily show, it. I mean, I just did. So now the question is, okay, if we had this angle, then we would need to show that really, what we need is to show that IB over, so IB over IC would need to equal, and this is a question mark, BR over CS. Okay, and now let's think. So what is BR over CS? So BR is the same as QA, and CS is the same as AP. So QA over PA. Okay, this is more reasonable. Or also QA over PA. We also know that these all are the same. This is also the same as QI over IP. And now the question is IB over IC the same as QI over IP? And this is in fact the same because this is just the power of point of I. IB times IP is the same as IQ times IC. So given this is true, that means that these two things are equal. But given this is equal to this is equal to this, that means that this is in fact equal. And so now what we have is similarity, and from that similarity, we have that this angle is equal to this angle, and we are done. And this solves the problem. Now, a different sort of motivation could have been potentially to say, well, this sort of way to like motivate this whole thing was say, well, fundamentally, like when you add in t, you really need to show that TRI is the same as TSI. And to be able to show that, what you really need is ISC to be equal to IRB. Okay, and now you say, okay, what do I need? But if this is true, like what, and then you can maybe go forwards and see like, wait, I have ICS is the same as IBR. So if my problem statement is true, then I must have similarity. Then these two triangles must be similar. So you try some angle chasing, you see, okay, you're not getting everything just by purely doing angle chasing. So then you go, okay, so I must find the similarity. And given I have this angle, given I have that IBR is equal to ICS, that means, okay, that means I need to look at BRCS is the same as IB over IC. And then simply you find out, okay, BR, what do I care about BR? Well, it's just equal to this. And then you realize, oh, QA, PA, I mean, there's multiple ways to finish it. I think this is the cleanest way to finish it. You could just do some trig here. I mean, as I mentioned, multiple ways you could end this. And this finishes up our problem. I think it's a nice little problem in geometry, a cool one to show just like basic understanding of, okay, what is it that you need at any point? Similarity is like very common in these introductory problems. If it's not just an angle chase, right? There's a bit of similarity. And yeah, I mean, that's done. I'm curious if you have any other solutions to this one. For me, this was this is just like naturally flowing to say like, okay, what's the next step? What's the next step? And finally, okay, we just finish up with similarity. But let me know if you have different approaches, different ways you thought about the problem in the comments below. And as always, thanks for problem solving.